Welcome to this explainer. Okay, look, if you build with LLMs, you already know that just tweaking your prompts is, well, it's not always enough to get reliable results, right? Today, we are diving deep into some seriously fascinating source material on advanced agentic design patterns using LangGraph. We're going to see exactly how to build and, more importantly, deploy these highly autonomous workflows. So, here's our roadmap for today. First up, we'll look at the limits of basic routing. Then move into the orchestrator and worker pattern. After that, we'll check out the evaluator and optimizer loop, jump into fully autonomous React agents, and finally, we'll cover how to get all this into the cloud. All right, let's kick things off with section 1, the limits of routing, or as I like to call it, the static receptionist. Think about it like walking into a doctor's clinic. You walk up, tell the receptionist your symptoms, and they check a rigid set of predefined conditions to figure out exactly where to send you. General physician, specialist, maybe you just need the lab? Now, they do a great job pointing you in the right direction based on those strict rules, but they aren't exactly doing dynamic problem solving. As a developer, if a user throws a totally weird, brand new scenario at your app, your AI receptionist is just going to freeze up. And that brings us to a really stark contrast. If we rely strictly on that basic routing for complex tasks, we hit a massive bottleneck. Picture trying to handle 1,000 different possible user requests. A static router would literally need thousands of rigid if-else statements to cover every single scenario. You'd have to hardcode everything. It just doesn't scale. You simply can't anticipate every single curveball a user might throw at you. We definitely need something smarter. Which leads us perfectly into section 2, the orchestrator and worker pattern, or the construction contractor. I absolutely loved this analogy from this source material. Instead of a receptionist, imagine the orchestrator as a general construction contractor. When a client hands them a blueprint, the contractor doesn't just pull out a massive book of if/else steps. Instead, they look at the unique requirements and dynamically hire the exact masons, electricians, and plumbers they need on the fly. The orchestrator AI does the exact same thing. It analyzes a complex prompt, figures out which specialized AI workers are needed, spins them up, and puts them to work. The real magic here is the parallel execution. It is absolutely killer for things like generating massive research reports. The orchestrator gets the task, creates the exact right number of workers, and fires them off at the exact same time. You've got one worker digging into market trends, another one drafting the intro, and maybe a third running technical checks, all operating totally independently. Then, a final component, the synthesizer, grabs all those individual pieces and beautifully merges them into one cohesive output. It's a brilliant setup for sure. But there is a catch. As we start delegating all these tasks to parallel AI workers, we run into a pretty massive challenge. What on earth happens when one of those AIs hallucinates or just makes a dumb mistake? Since they're running independently, one bad worker can totally derail the synthesizer's entire final report. And that brings us to section 3, the evaluator and optimizer pattern, also known as the strict teacher. Think of this like a really demanding teacher grading a geography test. A student hands in their paper, and if it scores below an 80%, the teacher doesn't just say, oh well, no. They hand it right back with feedback and force the kid to rewrite it until they actually meet the standard. Now, obviously, we don't want our AIs stuck in some infinite loop forever, so the framework lets us set a hard limit, say 25 attempts. If it still fails after 25 tries, we pull the plug. But this self-correction loop is exactly how the evaluator optimizer pattern works. To put this into code, imagine we ask a generator AI to write a witty poem about Python programming. It drafts the poem, then immediately hands it off to a separate evaluator AI whose sole purpose is to judge the humor. If the evaluator thinks it's completely dry and unfunny, it rejects it, spits out specific feedback on why it failed, and kicks it back to the generator. The generator tries again using that feedback, and they just keep looping until the evaluator finally gives it a passing grade.
Okay, moving on to section 4, React agents, which is really the absolute peak of autonomy.
You've probably heard the industry term React before, right? It stands for reasoning and acting. What's so game-changing about this architecture is how the AI constantly loops between reasoning about a problem, literally asking itself, okay, what do I need to do next to solve this, and then acting on it by using specialized tools. It's a continuous, self-driven cycle. So unlike your standard text generator, a React agent relies on 3 main components. First, you've got the brain, which is your LLM. Second are the tools. These are actual executable functions, like checking the current time, scraping a website, or hitting a database.
And third is the environment, which is basically the context where the agent operates and actually observes the results of whatever action it just took. To really put this into perspective, think about the difference between a simple LLM and a React agent. If you ask a standard LLM what time it is, it's just going to tell you it doesn't know. But if you ask a React agent, it autonomously reasons that it needs the time, takes action by calling its internal clock tool, observes the output, and then formulates a perfect answer for you. All of this happens entirely behind the scenes, no human intervention whatsoever. This is a massive deal because this level of autonomy lets your AI handle crazy, multi-step, completely unpredictable tasks all on its own.
Let's wrap things up with Section 5, Cloud Deployment, taking this from a local laptop to a production server. As the sources make very clear, having a genius agent running on your laptop is a cool proof of concept, but it's totally isolated. If you actually want to handle concurrent requests from hundreds of users, or make sure your AI remembers past conversations with persistent memory, your code has got to leave your local machine. You need to get it onto a robust server environment with a real framework. Luckily, deploying this stuff with LangGraph is surprisingly straightforward. It all basically centers around one configuration file, langgraph.json. You just define your agent's path and dependencies in there, run a couple of quick CLI commands, and boom! Your AI is suddenly exposed as live REST API endpoints, completely ready to be hooked up to any front-end app anywhere in the world. Plus, deploying it this way unlocks something really cool, LangGraph Studio. Look, if you've ever tried to debug multiple parallel agents through a plain text terminal, you know it is an absolute nightmare. Studio gives you a slick, visual interface. You can literally trace every single worker, every reasoning step, every tool call, and every state change in real time. It's a total game changer because you can finally see exactly why an agent made a specific decision. So as we wrap up this explainer, the leap from those strict, rule-based receptionists to brilliant, fully autonomous React agents is it's staggering. We now have the blueprints to orchestrate entire teams of AI, evaluate their work on the fly, and deploy the whole shebang at scale. Which leaves us with one incredibly exciting question. With all these powerful tools now at your fingertips, what complex workflow are you going to build next?